All right, welcome to Charlie's Engineering Corner. I am Charlie, and this is our motor lab behind me, and we're going to be working there today. This is part 4 of our basic industrial maintenance series, and today's topic is AC motors. All right, we are going to use some of the principles we learned earlier in the electromagnetism section. So you remember when we applied a current to the wire, we developed a magnetic field around the wire. Remember taking a compass and we ran it along the outside of the wire. Well, today we're going to use the same concept, and this time we're going to apply a rotating magnetic field that is developed by an AC current, and we're going to apply it to the motor. Okay, today's topics are, first up, we're going to talk about alternating current and what does the voltage look like if we plot it versus time. So we're going to look at the sinusoidal wave that's coming in and explain how that is used to magnetize the coils inside of an AC motor. Next thing we're going to do is look at two different single-phase motors. One is a split-phase motor, and the second is a capacitor start motor. We're going to show the difference between the two. In doing that, we're going to be talking about again, we're going to plot torque versus the RPM of the motor. As the motor begins to start, we have to apply a starting torque to the coils in the motor, and we're going to look at how that is generated in each one of those, the split phase and the capacitor. Next area we're going to talk about is the motor tag that's on the motor itself. The tags themselves have a lot of information on it. Make sure it's clear what each section of the tag is. And it's real important that you understand how to wire it up with the wire nuts inside the motor to the leads that come out of the motor. And the last topic would be the three-phase AC motors. We're going to explain how this AC waveform that we talked about, how that generates a rotating magnetic field inside the motor and allows it to operate. All right, alternating current. What does this voltage look like when we plot it versus time? Well, we need a special instrument, and that instrument is called an oscilloscope that's shown here on the right hand side. The instrument itself will plot the voltage that's coming in on your probe versus time, and it'll take a high frequency voltage and stretch it out so that you can see one cycle at a time or multiple cycles at a time, depending on what you got the time scale set at. So here on the left is a trace of one cycle that is coming in, and this is a trace of the single phase voltage. If we plot a single phase line coming in, the voltage, let's say, is 120 volts. Now, 120 is what's called RMS, root mean squared. It means that the average voltage for that sine wave is 120 volts. So if the average is 120, it must be the maximum is higher than that. Well, in fact, it goes from 0 to plus 170, back to 0, negative 170, and then back to 0. It makes one complete cycle, and that's called, one cycle per second is called a hertz, and it's doing that 60 times a second. So the common frequency here in the US is 60 hertz. Here we have a split phase motor circuit, as shown on the right hand side. The schematic shows that when we apply the single phase voltage at the top to neutral at the bottom, that we have two coils that are in parallel, the run coil here on the left and the starting coil here on the bottom. With a split phase motor, the resistance divided by the reactance of the start coil is always higher than that on the run coil. When we apply an alternating current to both the coils, the current in the start circuit is going to be higher than that in the run circuit. And by reactance, if you remember, reactance is the resistance offered by that the coils generate when an AC current is applied, and reactance is also measured in ohms. So now if you go ahead and you plot the torque versus RPM of each of these coils as the current is being applied, you'll see that the torque maxes out on the start coil before that on the run coil. In other words, at some RPM less than the maximum speed of the motor, the torque on the start coil occurs. Sometime later, when the motor is running at its rated RPM, then the torque on the run coil reaches its maximum. So there's this switch called a centrifugal switch that when the RPM of the motor is low, the switch would be closed. So most of the current is being developed in the start coil at the beginning at some RPM between startup and running speed. Then that centrifugal switch will open up, and then the torque that's generated by the motor is that occurs just on the run coil. Now we're going to take a look at the outside of the motor, specifically the tag that's on the outside of the motor. The tag has a lot of very important information on it, so I'm going to go through most of the items on the tag and explain what each item is. All right, looking at the left-hand side of this tag, the first thing we come across is the phase of the motor. This says it's a one-phase motor or a single-phase motor. So it's either going to be single-phase or three-phase. Next item is the operating frequency that the motor was designed for, in this case 60 hertz. Number three would be the operating RPM of the motor. In this case it's 3485. The frame size of the motor, this tells you the shaft diameter, mounting pattern of the foot, a lot of geometry of the motor. So if you go to the motor catalog, look up frame 56, it will give you all this geometry. Moving up to the middle here is the horsepower of the motor. This is a 1 horsepower motor. If you remember from our previous topic on power, power is equal to voltage times current, which are watts. This is 750 watts, or in this case, 3/4 of a kilowatt. Now, since power is equal to voltage times current, if we work at a low voltage, 115 volts, which is shown here. All right, so if we're operating at 115 volts, that's considered low voltage. We're going to be operating at 13.82 amps. That develops 1 horsepower. Now, if we take that to high voltage, basically double the voltage, then the current has to go in half. So the current at 230 volts would only be 6.6 amps. Number 8 is a type of enclosure. This is a ODP, which means open drip. There's various types of enclosures. You look in the motor catalog and you'll find totally enclosed, things like that. Then the last point I want to discuss on this part of the tag is the type of insulation that's used in this motor is K. It tells you basically how hot the motor can get before you destroy the insulation inside. All right, next let's zoom in on the wiring diagram that's used to connect up the motor itself to the single phase voltage in our case. All right, so on the left hand side is the low voltage circuit diagram. May not look like a circuit diagram, but it tells you the connections that you have to make between L1 and L2 to the motor wires inside. So the first connection would be L1 to T1, T5, and T3. So you make that connection with a wire nut. The next connection is T8, T2, and 7P2. Now those aren't connected to any wires on the outside, it's internal. And the last one you make is L2 to T4, L2 being the neutral wire. All right, from the outside of the motor, what we're talking about now is T4 is connected to L2, that's one wire nut, right? Next one would be T1 to T5 to T3 to L1. And you put a wire nut around that. Then the third wire nut is not connected to the outside, just the motor wires themselves. That would be T2, T8, and 7P2. Now you take those three wire nuts that you now have, you shove them into the little enclosure that they gave you, and you hope you don't short anything out, right? All right, the next single phase motor that we're going to discuss is the capacitor start motor. So just like we had with the split phase motor, we have the run coil in parallel with the start coil. So here's the run coil, and here's the start coil that has the capacitor in it. And just like last time, we're going to switch the start coil in and out of the circuit. We want to use the start coil at the beginning because the current going through the start coil is higher than that going through the run coil. So at low RPM, the start switch is closed. As we get up to RPM, as the centrifugal force opens up the switch, cuts out the capacitor and start coil, and then just operates on the run coil. So looking at the torque trace, which is here on the right, the red is the torque developed by the starting coil. The blue is the torque developed by the run coil. So you can see the torque generated by the start coil, because it has a capacitor in it this time, is much higher than what it is at the running stage here. So we will transition from, once we get just past the maximum on the start coil, we'll open up the circuit and then just rely on the run coil to keep it operating. All right, if you now look inside the motor itself, we've got two run coils like we had last time, and the third coil is attached to the capacitor. They're a little bit easier to see here on the right hand side. We got the two run coils that are also in parallel with the start, and then there's a capacitor. There are some capacitor start motors that actually use two capacitors, one to start it, and then the second one would be in the circuit during the run operation. So depends on your type of capacitor. All right, so we've gone through two single phase motors, the split phase and the capacitor. Now, the most common motor out there is a three phase induction motor. It is used throughout industry. It uses all three power phases that are coming in, and we're going to apply the fact that the AC voltage is increasing and decreasing. That means the magnetic field around the coils inside the motor are changing from north to south, 60 times a second. And then we're going to use one additional trick. The fact that the L1, L2, and L3 are coming in at the maximum voltages at different times. That's called phasing. All right, this time on the oscilloscope, we're going to bring in all three of the voltages and plot them at the same time. So we got phase A, which is connected to L1, phase B, which is connected to L2, and phase 3, which is phase C, which is L3. All right, now starting at time equals 0, you see the voltage on L1 is at its maximum. Voltage on L2 is 0, and the voltage on L3 is minus. It's the same absolute value as L1, but it's non-negative. All right, now inside the motor are 6 coils of wire on this particular motor, 6 coils of wire. We're going to pair them up so that the L1, which is phase A, we're going to say the top of the motor and the bottom of the motor are paired up diagonally. Phase C or L3 are paired up, and then the final one, phase B, are paired up. Now, why do we want to pair them up? Well, we're going to turn them into magnets. So if we apply this L1 voltage to this top coil, we're going to turn the top of the coil into a north magnet and the bottom coil into south. The same thing with the C coil. We're going to turn this one into a north pole, the opposite side into a south pole. Now, magnet B is not going to matter right at the moment because it has no voltage on it. So the A and the C coils they're both turned to a north magnet, and they're going to pull hard in the clockwise direction on the rotor. Now, the rotor, that's the center part of the motor itself, sometimes called a squirrel cage, because it has these bars, horizontal bars inside. Kind of looks like a hamster cage, if you want to call it. In any regard, it's made of these iron plates inside. Now, if you remember from our magnetism section, obviously iron and a magnet are attracted to each other. So when I magnetize these top two magnets, that magnetic field goes through the iron, and that's what develops the attraction here. All right, now let's look at it at 60 degrees later. Yeah, that's the same thing. That's 0 degrees. Now let's move on to 60 degrees here. All right, so when at 60 degrees, which is over here, you see the A phase is just basically shut off, it's 0, but the B and C phase are pretty high voltage. So the next two magnets in the sequence are now pulling hard on the rotor. And then the final one, 120 degrees, so we go over here to our graph. At 120 degrees, the C phase is no longer doing anything because it's 0 volts, but the B and A phase have pretty high voltage on them. So these two magnets are pulling hard on the rotor, and this just continues to go around. Well, it turns out the AC motor is very, very simple in terms of operation. There's very few mechanical parts inside. All we have is this rotor and the outside, which is called a stator. We got end caps on either end, which are not shown, but they have the bearings. The fact that we can use this rotating magnetic field, it automatically turns the coils into basically 3 northern magnets and 3 southern magnets, depending on the voltage that's being applied to the coil. So every 120 degrees, it repeats itself. So we start out at 0 degrees, then 120. Then we just start over again, go back to 60, and then 0. And it keeps repeating as it goes around. Now, how do you think we're going to make, as I indicated earlier, this is going to go clockwise. How do you think you're going to make it go in reverse, counterclockwise? Well, you probably already know this fact that if you switch any of these 2 phases around, then you change the current through the coil, and that will change the direction of the rotating magnetic field. Instead of going from A to C at the beginning, which is clockwise, it'll go from A to B, which is counterclockwise, by flipping the L2 to L1 or L3 to L2. And it's because the voltage that's being applied to the coil causes the magnet to reverse itself. So that concludes the AC motors. Thanks for watching, and we'll catch you on the next module.